It is February 25th, 2026. Welcome back to the Deep Dive. I'm your host, and joining me, as always, is our resident expert in all things Earth science.
Hello, everyone. Glad to be here for this one.
Yeah, so I want everyone listening to do something for me right now. Just for a second, put your feet flat on the floor. Or, if you're driving, just grip the steering wheel. Feel that solidity.
It feels incredibly stationary, right?
It does. It feels like the one thing in the universe you can actually count on to be totally still. But looking at the stack of sources we have today, that is a complete lie.
Which is famously the greatest deception in the history of human perception.
Exactly. Because the papers you've dropped on my desk this week, they are essentially a roadmap to a chaotic, churning, high-velocity engine room happening about 3,000 kilometers beneath our chairs. We aren't standing on a static rock. We're standing on the lid of a very intense pressure cooker.
We really are. And judging by the sources, the pressure's doing some pretty weird things right now. We have a mix of materials today that are frankly pretty heavy.
Yeah, I was looking through them, and it's a lot to unpack.
It is. We've got the high-level seismological studies from Wang and Vidal from 2024 and 2026 names that are causing some serious debates in the geophysics community right now regarding the rotation of the inner core.
And then we've got reports on something called the Gutenberg discontinuity, which sounds like a thriller movie title, but is actually a real place deep inside the Earth, plus some incredibly dense papers on mineral physics.
Right. Specifically about thermodynamics and what happens to iron atoms when you squeeze them with the weight of an entire planet. Oh, and we also have the Theia hypothesis.
Right, the one that suggests we might literally be standing on the corpse of an alien world.
Exactly. So our mission today is to connect all these dots. Yeah. To link the very small, like the quantum spin states of electrons in deep Earth minerals to the very large.
Like the rotation of the Earth itself and the length of our day.
Precisely. We need to unpack the invisible engine of the Earth.
So let's just jump right in. Let's start with the headline that basically freaked everyone out a couple of years ago. I remember seeing this everywhere. The articles were saying Earth's core is stopping, or Earth's core is spinning backwards.
Oh, I remember those.
My aunt actually sent me a link asking if she should buy canned goods or something. But looking at the actual data from these recent 2024 and 2026 studies, that is not quite what's happening, is it?
No, it's really not. Honestly, the stopping headline drives seismologists completely crazy. To understand what's actually happening down there, we have to talk about differential rotation.
Okay, let's unpack that.
It is the foundational concept here. Let's just visualize the architecture of the planet for a second. You have the crust, which is the thin, rocky skin we live on. Below that is the mantle.
Which is about, what, 2,900 kilometers deep?
Roughly, yes.
Right.
2,900 kilometers of solid but very slowly flowing rock. It's hot, and it deforms over millions of years. Then you hit the outer core. This is liquid iron and nickel.
So it's literally an underground ocean of molten metal.
Exactly. It flows like water. Well, it has a very low viscosity.
Yeah.
And floating in the absolute dead center of that liquid ocean is the inner core.
A completely solid ball of iron and nickel.
Right, with a radius of about 1,220 kilometers.
Yeah.
So it's basically a moon-sized crystal floating in a sea of liquid metal.
And because it's floating, it's not actually bolted down to the rest of the planet.
Precisely. Because it's decoupled by that fluid layer, the inner core can spin at a completely different speed than the mantle and the crust. It is an independent rotor inside the engine.
Okay, but this is where I get completely stuck. How on earth, pun fully intended, do we measure the rotation speed of a ball of iron buried under 3,000 miles of rock?
It's a great question.
I mean, we can't see it. We can't just stick a speedometer on it. We've barely scratched the crust with our deepest drill holes, so we certainly aren't sending probes down there.
No, we are definitely not. And this is where the sheer genius of the Wang and Vidal studies comes into play.
Yeah.
They didn't use probes. They used repeating earthquakes.
I looked this up in the notes, and this honestly blew my mind. These aren't just random tremors happening anywhere.
No, they are highly specific. Repeating earthquakes are quakes that occur on the exact same patch of a fault line, sometimes decades apart.
Like the exact same spot.
Think of a fault line like a jagged metal zipper. There might be one stubborn tooth that gets stuck. It builds up stress over time, it finally slips and causes a quake, and then it gets stuck again. Years later, it breaks in the exact same way, at the exact same location.
Producing what the papers call a waveform doublet.
Yes, a doublet. It's effectively a seismic fingerprint. Now, if the Earth were just a static, solid block of stone, A quake in 1991 and a quake in 2023 from that exact same stuck zipper should send identical sound waves through the planet.
Right, so a seismometer on the exact opposite side of the planet should record the exact same squiggly line.
The signals should perfectly overlay, but they didn't.
They didn't match.
They were different. The waves changed their shape and their arrival times. And because we know the earthquake spot didn't move and the seismometer on the other end didn't move, the only variable, the only thing that could have changed the wave—
Is the stuff the wave actually traveled through?
exactly, the inner core moved. It rotated to a different orientation between 1991 and 2023.
Because the inner core isn't a perfect smooth sphere, right? It has texture.
Right, it has topography and density variations. We call it heterogeneity. As it rotates, it presents a different face to the seismic waves passing through it. So by analyzing 121 of these repeating events, mostly from the South Sandwich Islands over those 3 decades, Wang and Vidal basically built a timeline.
And this is where the term superrotation comes in. This was the status quo for a while, right?
It was. In the early 2000s, the data suggests the inner core was superrotating. That simply means it was spinning slightly faster than the mantle and the crust.
So if you were standing on the inner core, which obviously you'd be crushed and vaporized immediately, but if you were, you would be slowly overtaking the people up on the surface.
Right, you'd be racing ahead, about 1/10 of a degree per year faster. But then around 2010, and this is what the recent 2024 to 2026 papers really confirm, it hit a major turning point.
It slowed down.
It slowed down. It essentially synchronized with the mantle for a brief moment.
Yeah.
And now, based on the most current analysis, it is subrotating.
Meaning it's lagging behind us, it's moving slower than the surface?
Slightly slower, yes. But here is the kicker, and this is why I love this specific data set. This isn't just some random chaotic drift. It looks like a predictable oscillation.
A cycle.
Yes, roughly
Yeah.
a 7-decade cycle of speeding up and slowing down.
Which implies a tug of war, doesn't it? I mean, if something speeds up and slows down, there have to be forces pushing and pulling on it. Newton's laws still apply, even down in the absolute hellscape.
Indeed, they do. There are 2 massive forces at play here. First, you have the magnetic field, which is generated in the liquid outer core. That magnetic field grips the solid inner core and tries to spin it.
So that's the electromagnetic torque, the engine pushing it forward.
Right, but then you have the mantle. The mantle is overwhelmingly huge and heavy, and it's physically lumpy. It has gravitational anomalies. These massive anomalies pull on the inner core, trying to lock it into place.
So that's the gravitational torque. The magnetic field is trying to spin it up, and the heavy, lumpy mantle is trying to drag it back. And what we are seeing in the seismic data is the result of that wrestling match.
Exactly. And right now, the gravitational drag is winning. The core is slowing down relative to the surface.
And that drag actually has consequences for us right up here on the surface because of the conservation of angular momentum, right?
It's the classic law of the playground roundabout.
Yeah.
If the kid sitting in the middle of the roundabout leans out or slows down, the whole roundabout speeds up to compensate. The Earth is a closed system. You cannot create or destroy momentum.
So if the incredibly heavy iron core slows down, the lighter rocky crust has to speed up to keep the total momentum of the Earth constant.
Which logically shortens the length of the day.
Okay, so when we say shortens, are we talking about me getting to leave work early today?
I'm afraid not. We are talking about variations measured in milliseconds, thousandths of a second.
So I definitely can't use that as an excuse for being late to a meeting. Sorry, boss, the inner core is subrotating. My alarm clock is calibrated to the mantle.
Yeah, I highly doubt that would fly with HR.
Yeah.
But from a scientific standpoint, it is measurable. The length of a day fluctuates constantly anyway due to atmospheric winds, ocean currents, and the gravitational pull of the moon.
Right.
But the core's contribution is distinct. In fact, the data shows a 5.9-year oscillation cycle in the length of a day that correlates almost perfectly with variations in the magnetic field.
So the magnetic field and the day length are essentially dancing to the same beat.
They are deeply interconnected. It is a highly complex web of electromagnetic and gravitational coupling. The real takeaway here for anyone listening isn't that our clocks are broken, but that the Earth is a dynamic system. It is shifting and oscillating beneath our feet right now. The ground is not static. It has a pulse.
It's really humbling to think about. We think of the ground as the most stable thing in our lives, but 5,000 kilometers down, it's a completely different story. Now, moving up from the core, we hit that boundary I mentioned earlier, the Gutenberg discontinuity.
Yes. At roughly 2,900 kilometers depth, this is formally known as the core mantle boundary, or CMB.
Discontinuity just sounds so dramatic. It sounds like a break in the space-time continuum or something.
In seismology, a discontinuity is simply a sharp, measurable change in the behavior of seismic waves. And this is by far the biggest one inside the planet. It was discovered by a seismologist named Benno Gutenberg back in 1914.
Because before that, we didn't really know exactly where the core began, did we?
No, we had estimates, but he pinpointed it.
How did he find it with 1914 technology?
Essentially by listening to the silence. When an earthquake hits, it sends out different types of waves. The two main ones are P waves, which are primary pressure waves, kind of like sound traveling through air,
Okay.
and S waves, which are secondary shear waves. Shear waves shake the ground side to side. Now here is a fundamental rule of physics. You cannot shear a liquid.
Right, because if you try to shake water side to side, it just flows. It doesn't snap back into place like a solid rock would.
Exactly. So Gutenberg noticed that at a certain specific distance from the epicenter of an earthquake, the S waves just vanished. They hit a wall they couldn't pass through.
And that shadow zone where no S waves appeared proved that the Earth had a liquid layer.
Yes. It proved the outer core was molten. And the conditions at this boundary are just staggering.
Yeah, I read in the notes that it's essentially a wall of fire.
It is extreme. You have the solid silicate rock of the lower mantle sitting directly on top of the swirling liquid iron of the outer core. The temperature jump across that boundary is massive. The liquid core is something like 700 degrees Celsius, hotter than the solid mantle right above it.
That is a huge temperature gradient over what is relatively a very short distance. It's like putting a frozen frying pan directly onto a blazing stove element.
And that intense heat flow drives everything. It boils the bottom of the mantle. But the boundary itself isn't flat. For a long time, we model it as a perfect smooth sphere. But modern seismic tomography shows it has major topography.
Like valleys and mountains.
Yes, upside-down mountains, if you will. There are huge undulations valleys that are up to 5 to 8 kilometers wide. It's a rugged, chaotic landscape where the rock meets the molten metal. And right above this rugged boundary is a highly active region called the D double prime layer.
D double prime. That sounds like a terrible math grade I once got.
It's a bit of an archaic naming convention, but it refers to roughly the bottom 200 kilometers of the lower mantle. In geophysics, we often refer to it as both the graveyard and the birthplace.
Let's break that down. Graveyard, I assume, means dead things, but geological dead things.
Yes, it is where subducted oceanic slabs, these are huge pieces of the ocean floor that got pushed onto the continents millions of years ago by plate tectonics. They sink all the way down through the mantle and finally come to rest there. It's a literal graveyard of ancient oceans.
So the floor of the Pacific Ocean from, say, the Jurassic period might be sitting down there right now.
It is very likely, yes. It slowly sinks to the viscous mantle, hits the core boundary, and just piles up into these massive heaps of cold, dense rock.
And the birthplace part.
It is where we think mantle plumes originate. Hot material right at the boundary gets heated by the core, becomes buoyant, and eventually rises up through the mantle like a bubble in a lava lamp.
And when it hits the surface, it creates hotspots.
Exactly. Places like Hawaii or Iceland.
So the volcanic islands of Hawaii effectively started their journey at the Gutenberg discontinuity.
That is the leading consensus, yes. It is a massive planetary conveyor belt of destruction and creation. The old crust dies at the bottom, and new islands are born from that same depth.
That is a perfect segue into our third section, because when we look closely at this graveyard layer, we find something even bigger than just old crushed tectonic plates. We find the blobs.
The LLSVPs. Large, low shear velocity provinces.
Let's just stick with blobs for a second, or the actual names scientists gave them, which I love, Tuzo and Jason.
Yes, they are named affectionately after Tuzo Wilson and Jason Morgan, who were two absolute pioneers of plate tectonic theory. Tuzo's the mass located beneath Africa, and Jason is the one sitting beneath the Pacific Ocean.
And when we say large, we really aren't kidding around. How big are these structures, actually?
They are truly continent-sized. They extend laterally for thousands and thousands of kilometers across the core mantle boundary, and they rise up vertically up to 1,000 kilometers high.
That is massive.
Collectively, they make up about 8% of the entire mantle's volume. That translates to roughly 6% of the entire Earth.
So 6% of the planet you are standing on is made of these two bizarre, anomalous structures. Why do scientists call them low shear velocity provinces?
It comes back to the seismic waves again. When those shear waves pass through these specific regions, they slow down significantly. In seismology, slow usually implies one of two things. Either the material is exceptionally hot and therefore less rigid, or it is chemically different from the surrounding rock.
So for a long time, people just assumed, oh, it's just a thermal plume. It's just a big blob of hot rock waiting to rise.
Right, they thought it was purely thermal. But as our imaging techniques have gotten better, the tomography has improved drastically, and we now see that these blobs have incredibly sharp edges.
And why does a sharp edge change the theory?
Oh, if it were just a heat anomaly, you would expect a gradual fade, a smooth gradient. Like if you hold your hand near a campfire, it gets gradually warmer as you move closer.
Right, it doesn't just go from freezing to burning in 1 millimeter.
Exactly. But a sharp seismic edge strongly suggests a distinct change in the actual material, a chemical difference.
So they're distinct piles of foreign stuff. I think the papers use the term thermochemical piles.
Yes, they are denser than the normal mantle rock around them, which is why they stay anchored to the bottom. They are effectively heavy, gigantic piles of sludge.
Which naturally leads to the origin story. And this is frankly the most sci-fi part of this whole deep dive. Where did these continent-sized sludge piles come from?
There are two main competing hypotheses. The first one connects right back to the graveyard idea we just talked about. Some scientists argue they are simply the result of billions of years of subducted oceanic crust that piled up, melted together, and formed these dense chemical anomalies.
So that's the dust bunny theory of the Earth's mantle. We've just been sweeping old tectonic plates under the rug for 3 billion years until they formed a mountain.
In a simplified way, yes. But the second hypothesis is gaining a lot of serious traction, especially with recent studies comparing isotopic signatures.
Yeah.
This is the giant impact hypothesis.
The Theia impact.
Yes. The leading theory for how our moon formed is that a Mars-sized protoplanet named Theia smashed directly into the early proto-Earth about 4.5 billion years ago. The massive debris cloud from that collision coalesced to form the moon.
But obviously not all of Theia got blasted into space.
Correct. New geodynamic simulations, specifically those run by Yuan and his team recently, suggest that huge chunks of Theia's mantle could have survived the impact. Because Theia's rock was significantly denser and richer in iron oxide than Earth's, it could have punched straight through Earth's global magma ocean.
Like heavy bullets dropping through water.
Exactly. They sank all the way down, and because they were so dense, they didn't mix well with the rest of the mantle. They just settled at the very bottom, resting right on top of the core.
So Tuso and Jason might literally be the corpses of an alien planet.
Alien in the sense of another planetary body, yes. They very well might be the physical remnants of Theia resting deep inside the Earth for 4.5 billion years.
That just blows my mind. Like, you know, we look up at the night sky at the moon and say, oh, wow, that's part of the Great Collision. But we look down at our own feet, and the other half of the collision is right beneath us. We are standing on a chimera planet. It's Earth plus Theia.
And what's fascinating is that the evidence is hidden in the chemistry of the rocks on the surface. When geochemists look at ocean island basalts, which is the lava that erupts from places like Hawaii or Samoa, places fed by deep plumes originating right near these blobs.
Right.
That lava has a very strange isotopic signature.
The notes mention different ratios of noble gases like helium-3 and neon isotopes.
Yes, ratios that are remarkably similar to what we see in lunar rock samples brought back by the Apollo missions.
See, that is the smoking gun. The lava bubbling up in Hawaii matches the rocks sitting on the moon because they both originally came from the exact same parent body, Theia. One piece was thrown into the sky, and the other was buried 2,900 kilometers deep.
It is a deeply compelling link. It directly connects the deep, isolated Earth to the violent, chaotic history of the early solar system.
Okay, so we've got spinning solid cores, we've got alien planetary blobs. Now we need to zoom in, way, way in, from the size of continents down to the size of individual atoms. Section 4 of our dive is about the quantum shift.
This is where the field of mineral physics becomes crucial. To truly understand the lower mantle, we have to understand what happens to basic minerals under extreme, unimaginable pressure. We are talking about millions of atmospheres of pressure.
And the specific mineral in question here is called ferropericlus.
Right, ferropericlus. Its chemical formula is MgVO. It is a mixture of magnesium oxide and iron oxide, and it happens to be the second most abundant mineral in the entire lower mantle. The really interesting player in this crystal structure is the iron.
Because iron atoms have electrons doing weird things.
Specifically, their third electrons. In a normal low-pressure environment like here on the surface, these third electrons naturally repel each other. They spread out into different orbitals to maximize their distance. We call this a high-spin state.
So it's kind of like a city bus where everyone sits in their own separate row because they want their personal space.
That is a perfect analogy. High spin equals demanding personal space. But as you go deeper into the Earth, the physical pressure builds relentlessly. It literally squeezes the atoms closer together. Eventually around 50 gigapascals of pressure, which occurs in the mid to lower mantle, the crystal field energy overpowers that natural electron repulsion.
The pressure essentially forces the electrons to pair up.
Right, it forces them into the lower energy orbitals. They have to share seats on the bus.
They undergo a quantum flip. They go from high spin to low spin. And the crazy part is when they finally pair up, the iron atom itself literally shrinks.
Yes, the ionic radius visibly decreases. This leads to what mineral physicists call a volume collapse. The mineral ferropericlus suddenly becomes denser by about 2 to 4% entirely because of this quantum spin change.
Now, 2 to 4% sounds like a tiny rounding error, but when you apply that to an incredibly massive layer of the Earth,
It matters immensely. It creates a much denser, more compact lower mantle. And crucially, it completely changes how sound travels through the rock.
we're back to the seismic waves.
Yes. Sound travels significantly faster through this compacted low-spin iron. Both the compressional P waves and the shear S waves see their velocities jump up.
Which means if seismologists didn't know about this quantum shift happening in the atoms, they would completely misinterpret the data.
They absolutely would. They might look at the fast seismic waves and mistakenly think the rock down there is much colder than it actually is, just because the sound is moving faster. You have to account for the quantum state.
It also completely changes how heat moves through the mantle, right? This seemed like the most critical part for our whole engine room analogy.
It alters it significantly. Low-spin iron has drastically reduced radiative thermal conductivity.
Let's break that down for the listener. Radiative thermal conductivity.
Sure. Heat moves in three primary ways: conduction, convection, and radiation. In the deep, deep Earth, the rocks are so unbelievably hot that they physically glow. They radiate heat as infrared energy, just like the glowing orange coils in a toaster.
Okay, that makes sense.
In the normal high-spin state, iron is quite good at absorbing and transmitting that infrared radiation. But when it gets crushed into the low-spin state, its absorption bands fundamentally shift. The material changes its optical properties.
So it becomes more opaque.
Exactly. It becomes highly opaque to heat in certain infrared frequencies. It blocks the heat transfer.
So the lower mantle acts like a giant thermal blanket.
Or a closed window, depending on the exact frequency. But essentially, the quantum spin transition alters the throttle of the Earth's internal engine. It physically dictates how fast the immense heat from the core is allowed to escape into the mantle.
And heat is really the name of the game here, which brings us perfectly to our final major topic today, powering the machine. Because if the heat can't get out, or worse, if the core runs out of heat, we are in serious trouble.
The energy balance problem.
Yeah.
This is one of the classic thermodynamic puzzles in all of Earth science.
We know the core is incredibly hot, and we know it's slowly cooling down over billions of years. That cooling process drives the convection currents, which in turn drives the magnetic field.
Correct. The geodynamo, the vast swirling generator of our magnetic field, requires a massive amount of continuous power. We have a few main sources for that energy. Number one is secular cooling. That is just the leftover primordial heat from the violent formation of the Earth slowly bleeding away.
The heat from the original planetary accretion and giant impacts.
Exactly. Number two is latent heat. Remember, the inner core is actively freezing. It is solidifying from a liquid into a solid ball. Just like water turning to ice, that phase change releases latent heat into the surrounding fluid.
And number three is compositional energy.
This is a massive driver. As the liquid iron freezes onto the solid inner core, it is mostly pure iron that crystallizes out. It rejects the lighter chemical elements that are mixed into the outer core, things like oxygen, sulfur, and silicon.
So these lighter elements get left behind in the liquid.
And because they are lighter than the surrounding iron, they immediately float upward.
Like carbonation bubbles rising in a glass of soda.
Yes. And that constant upward rising motion heavily stirs the pot. It adds massive gravitational energy to the convection currents. So these three things combined, thermal cooling, the latent heat of freezing, and the compositional stirring power, the geodynamo.
But there is a massive paradox mentioned in the thermodynamic papers, the paradox of the inner core age.
Right here is the core of the problem. We know for a fact that the Earth's magnetic field has existed for at least 3 billion years. We have hard evidence in ancient rocks, a field called paleomagnetism that shows magnetic minerals aligning to a strong global field way back then.
Okay, so the protective shield has been up and running for 3 billion years.
But when thermodynamicists do the complex math on how fast the core needs to cool to maintain that field, It suggests that the solid inner core is actually quite young.
How young?
Geologically speaking, very young, perhaps only a half a billion to maybe a billion years old.
Wait, hold on. If the solid inner core didn't even exist until a billion years ago, that means for the first 2.5 billion years of Earth's history, we didn't have that compositional kick from the light elements rising.
Exactly right. We didn't have the latent heat of freezing either, because nothing was freezing. So the early dynamo had to be powered exclusively by secular cooling. It was just relying on the planet getting colder.
Which, as you said earlier, is much less efficient.
It is terribly inefficient. To maintain a strong magnetic field by pure thermal cooling alone, the core would have to be cooling down extremely fast. If you run those numbers backward in time, it means the early Earth would have been impossibly hot.
Like totally molten everywhere.
The whole mantle would have been a global magma ocean.
But we know that isn't true because we have solid crystal rocks that are 3 or 4 billion years old. So either our math is fundamentally wrong or we are missing a massive unseen energy source.
And this brings us to a concept called ohmic dissipation.
That sounds like electrical resistance.
It is precisely that. The massive electric currents that generate the magnetic field encounter natural resistance as they flow through the liquid iron. That resistance creates waste heat. We call this ohmic dissipation. Think of how a laptop charger gets really hot when it's plugged in.
Oh, okay.
We used to think this waste heat value for the core was relatively low, but recent high-pressure experiments suggest it might actually be extremely high. Maybe 1 to 2 terawatts of waste heat?
So the dynamo is essentially an absolute gas guzzler. It burns a tremendous amount of energy just to keep itself running.
Exactly. And if it burns that much energy, the core must be cooling even faster to provide it, which ironically makes the young inner core problem even worse. It creates a thermal history for the planet that completely contradicts the geological record.
So how do geophysicists fix it? How do we keep the magnetic field alive for 3 billion years without completely melting the early Earth?
One of the leading theoretical solutions is radioactivity.
You mean putting a nuclear reactor inside the core?
Essentially, yes. Elements like potassium, thorium, and uranium. We usually find these radioactive elements in the rocky crust and mantle. But if a small fraction of potassium, for example, managed to partition into the metallic core during the Earth's chaotic formation, it would provide a steady internal heat source.
Like a slow-burning log on the fire that keeps the heat up without requiring the whole planet to cool down so fast.
Exactly. It would mean the core doesn't have to cool as rapidly to generate the exact same dynamo power. It neatly solves the thermal history paradox.
Is there actual physical evidence for radioactive potassium in the core?
It is hotly debated. High-pressure lab experiments show that potassium can technically alloy with iron under extreme pressure, so it is chemically possible.
Yeah.
But honestly, even factoring in radioactivity, the strict thermodynamics still strongly suggest the inner core is relatively young.
So that giant solid iron ball in the dead center might actually be a newcomer to the planet.
It is highly likely that the early magnetic field was started purely from thermal cooling, and then the inner core finally nucleated much later, maybe just in the last billion years.
And when it finally started freezing, it kicked in the compositional convection, just as the thermal cooling was starting to run out of steam.
It was a perfectly timed Saved by the Bell moment for Earth's magnetic field.
It is amazing how fragile that planetary balance sounds. If the timing had been off by just a little bit, maybe Mars happens here. Maybe our magnetic field dies. The solar wind strips our atmosphere away, and we aren't sitting here having this deep dive conversation today.
It is a very real possibility. The complex interplay of heat density and quantum spin is the only thing keeping the shield up. If the inner core hadn't formed right when it did, the dynamo very well might have collapsed entirely.
Wow. So let's try to synthesize this whole journey we've been on. We've gone from the absolute center of the Earth to the microscopic quantum level.
It really is a deeply connected system. If you think about it, you have unimaginable pressure crushing individual iron atoms into a low-spin state deep in the lower mantle. This fundamentally changes the density and thermal properties of the rock. That density affects how these massive LLSVP blobs, which are potentially ancient alien planetary fragments, sit heavily on the core mantle boundary.
And those massive blobs act like thermal blankets insulating the core or funneling heat in highly specific ways.
Which then directly dictates the heat flow out of the liquid outer core. That specific heat flow is what drives the turbulent convection of the geodynamo.
And the geodynamo generates the magnetic field.
And finally, that magnetic field interacts electromagnetically with the solid inner core, causing it to constantly speed up or slow down, which ultimately changes the length of our day by tiny fractions of a second.
It's an incredible domino effect stretching from the quantum state of a single atom all the way up to the planetary level.
And we were just casually standing on the surface, checking our watches, completely unaware of the massive, chaotic engine grinding away beneath us.
It really completely changes how you look at a compass. It's not just a needle pointing north, it's pointing to this swirling, cooling, spinning, radioactive mystery room.
It absolutely is. And here's one final thought to leave you with. We spent a good amount of time today talking about the blobs being the shattered remnants of Theia.
The giant impactor.
Right. If that hypothesis holds up to further scrutiny, it means that Earth is a literal chimera.
A mix of two entirely different bodies.
Yes, we aren't just living on Earth. We are living on Earth plus Theia. Those alien pieces didn't just vanish. They are still down there. They are distinct, they are massive, and they are actively affecting our geology today.
That is wild. We always look out to the stars to find alien worlds, but there are continent-sized islands of an alien world buried 3,000 kilometers straight down under our feet.
And the ground beneath us isn't just dead, static rock. It's breathing, or at the very least, it had a heartbeat, a rhythm of rotation that constantly speeds up and slows down, subtly altering time itself.
A fiercely dynamic planet through and through. Next time you watch a sunset, just remember that the planetary rotation making that beautiful sunset happen is actively being tweaked by a heavy metal ball floating in a hot ocean thousands of miles down. Huge thanks to our expert for guiding us through the layers today.
My pleasure. Always happy to dig deep into this stuff.
And thank you for listening. Keep looking up at the stars, but definitely don't forget to wonder about what's going on deep down below. We'll catch you on the next deep dive.